Hi everyone, I'm Ray from UIUC. Today I'm going to introduce how to make our smart home more reliable, predictable, and safe with our system SafeHome. This is a collaborative work with Microsoft Research. In the smart home world, we have many kinds of smart devices such as smart light, smart fridge, and extra. The smart devices we refer here are those who can connect to the networks and be accessed and controlled by home automation systems. Let's just think about when we are setting up or using smart devices, what are in our minds? Controlling a single action of a specific device? No, we want to control our lives. We want to make our lives easier. Then, how do people control smart homes nowadays? Either through command, for example, make espresso, or through routine, which is a sequence of commands on the same or usually different devices. For example, make an espresso and make a pancake. The status quo system executes commands and routines in a best effort way. They instantaneously attempt what are initiated, no matter what is running or whether there's any failure. However, such way of execution misses two natural expectations from users. When users put a bunch of commands in a routine, they expect to execute them all together. This is essentially atomicity, which is a well-known property. Another expectation is that when two different routines touching the same devices are triggered together, people expect them to run isolated, so that their results do not affect each other. By that, we mean we want the system outcome to be equivalent to the routines being executed one after another, which is serial equivalence. A simple example is a scenario with a routine that opens the garage door, moves the trash can out, and closes the door. At the meantime, if another routine of closing garage door is triggered, but before trash can move out, the trash can will not be able to get out for garbage collection, or even worse, hit the door. Here, users will strongly expect these two routines to run one after another. However, such guarantee is poorly supported in nowadays systems. In our exploration with TP-Link smart clocks, the interleaved execution occurs unignorably. Another missing support is long-running routines, which have long-running intents from the users or by the device actions themselves. This brings extra challenges for a system to provide user-facing atomicity and isolation. Thus, we propose SafeHome, a home automation system that supports long-running routine expression, can properly isolate concurrent routines through providing serial equivalence, and can ensure routine execution atomicity. The key and unique challenge for SafeHome is that every system action is immediately visible to users. Any delay or device state change has higher physical world impact compared to non-smart home systems. Thus, in SafeHome, we introduce four visibility models. They provide a spectrum between latency and temporal incongruence, which we will introduce later. In the models, we utilize lock-based mechanisms with leasing designs to help routine scheduling and execution. The visibility model we proposed include weak eventual, partitioned strict, and global strict. Let me introduce them with an example. We have 5 routines touching 4 devices. We colored these devices differently. 3 of the routines are initiated by 3 residents of the house to cook different breakfast. 2 other routines are sensor triggered to clean the living room or the kitchen. All routines are triggered at the same time, and we assume each command needs to run one time unit and run sequentially inside one routine. Let's take a look at the status quo design. We call it weak visibility model. It executes routine immediately when it triggers. Thus, all routines execute in parallel and can finish in 2 time units. However, sending 2 commands simultaneously to one device may cause errors. For example, the first command may get interrupted, or more commonly, the second command gets ignored. If we don't want to see these potential errors, the strictest way is to only execute one routine at a time. We call it Global Strict Visibility Model. It takes 8 time units to finish. GSV is very strict, but is still useful in those cases with resource constraint like energy. When there are limited maximum power supply, GSV can guarantee that the circuit breaker does not trip. However, GSV is too strict in most cases. Thus, a slightly less strict model would be partitioned strict visibility model. It allows routines touching disjoint devices to execute in parallel. This model can finish our example in 5 time units. PSV is useful when the commands have implicit dependencies, so the users expect the whole routine to execute without interference. However, PSV can still take tens of minutes to execute with those long-running routines. Thus, it's still not ideal. Then can we do better? Look back to our examples. Even for the routines touching the same devices, we can still place them in a way so that they can execute in parallel and follow some serial order. In the example placement shown here, it takes 3 time units to finish, and the 5 routines end with the system state equivalent to if running them in order 3, 1, 2, 5, 4. This is eventual visibility model that we have. The way we achieve this design is by using locks. Note that the locks here are all held at the central device. All SafeHome logics sit here. No code is needed at other smart home devices. So goes back to our EV model. Each routine holds the locks for the device it touches, but can lease them out under certain conditions. The intuition of leasing is to pipeline the routines when device is idle. We support post-lease and pre-lease. In post-lease, if a routine is done with a device, it does not have strong need to lock it anymore, so it can lease the locks out. For example, after R1 has finished making the coffee, it can let R2 start. The serial order under post-lease is always laser happens before lazy. With a similar intuition, in pre-lease, if a routine has acquired a lock but has a while before it accesses the device, it can lend the lock to another routine which uses it and returns it. This happens to the pancake maker in R1, where EV can start R3 immediately. In pre-lease, the serial order is always lazy happens before laser. In summary, EV model can provide short waiting time and a serial equivalence guarantee. But in the middle, there might be times that violates serial equivalence, which we call temporary incongruence. As in our example, pancake and coffee maker cannot be both on under any serial order. However, such incongruence is only temporary. It will get fixed automatically at the end, and that's why we call this model eventual. SafeHome manages the logic of EV with lineage table. It maintains at each time which routine will access which device, so that the execution can follow a potential serial order. Here is a lineage table, for example. Each table entry is marked with a status of holding the device access, scheduled, lock leased out, or lock released. SafeHome handles dynamically arriving routines. I described a static scenario here just for simplicity. Also, to reduce search space, SafeHome utilizes backtracking to decide valid routine placement. We also explore 2 other scheduling policies of first come, first serve, and just in time. If you are interested in more details on these slides, welcome to read the paper. So far, the designs are focusing on the serial equivalence, but there's another property that we care about, which is atomicity. It relates to the design when failure happens. A naive way to provide atomicity is rollback, but it might cause high physical world impact. Thus, SafeHome minimizes rollbacks by serializing the failure and restart events together with the routine execution. Here is how it works in EV. If the routine does not touch the failed device, we can serialize it in arbitrary order. If the routine has finished with the device and the failure happens afterwards, this result is equivalent to serializing the routine before the failure. Similarly, if the device fails or recovers before the routine touches it for the first time, we can serialize the routine after the failure or restart. If the device fails when routine is touching it, we have to fail the routine itself. We have implemented our SafeHome with around 2,000 lines of Java codes with long-running routine support. It also supports the integration with TP-Link plug and Vimo. We did experiments for both deployment and simulations. They provide nearly the same performance, so we focus on simulation results here. We explored our model with real-world benchmark, in which we derived the morning and party scenarios from IoT bench test suite. We also extended our evaluation to a factory assembly line for a broader exploration. Besides, we did workload-driven experiments with an average of 500,000 runs for each configuration. In the evaluations, we measured multiple metrics, but here we focus on the end-to-end latency, temporary incongruence, which measures the incongruence of intermediate state, and the final incongruence, which measures the incongruence of system end state. We can see that the green line EV is almost as fast as the statistical system WV. EV provides comparable but slightly better temporary incongruence to WV, but the incongruence in EV is only temporary. When routines are done, EV can fix this incongruence and provide serial equivalent end state. However, WV cannot. We also find out and evaluate how pre and post lists reduce latency with the cost of temporary incongruence. When both mechanisms are off, SafeHome runs with longer latency but zero temporary incongruence. If both mechanisms are on, the routines finish with shorter latencies but higher temporary incongruence. In summary, SafeHome is the first step to provide reliability from a routine execution level. It provides 4 visibility models, among which EV model provides the best of both worlds with good responsiveness and strong guarantee. Our proposed lock leasing mechanism can improve latency up to 4 times. Here is my presentation for SafeHome. Thanks for listening.